Hello and welcome to Haybridge High School Maths Department Year 2 Pure Chapter 3 series, where today we're looking at the fantastically titled Sums to Infinity, which sounds, it's another one of those math topics that sounds like a prog rock album. It's another joke to ask your dad about or your mum. Right, okay, so before we get started on Sums to Infinity, let's have a look at something that I'm just going to tell you about beforehand, and that's Divergent and Convergent series. Now, a Divergent series is a series that tends to get towards plus or minus infinity, so it's going to get bigger and bigger all the time. So let me give you an example of one. If you had 1 plus 2 plus 4 plus 8 plus 16 plus dot dot dot, that number, each time you add a term, the answer gets bigger and bigger. So this is a divergent series. But with other series, what we find out that happens is that if we just show you this one, 1 plus a quarter plus a 16th plus 1 over 64, this particular series is heading towards 1 value, and we'll find out, let me just write that again, that should say convergent, but it's heading towards 1 particular value, and we'll find out in a bit how to work out what that particular value is. But we have, for now, all I need you to understand is that you get terms, series where it just keeps on getting bigger and bigger and bigger, and that is divergent, and ones that head towards a particular value, so we kind of narrow in on a particular value, are convergent. We're particularly interested in convergent series today. That's what's going to pique our interest today. Right, so here's a statement for you. A geometric series is convergent if and only if mod r is less than 1, where r is a common ratio. Now, that's not a typo by me. I've written if, and it's a if with a double F. Now, that means if and only if, which means something in particular for maths. Let me break down this sentence that we've got here. A geometric series is convergent means that the common ratio has to be between minus 1 and 1. This mod sign here, you could write this whole here as r between minus 1 and 1. Now, what the whole sentence is saying is, if you have a convergent series, then that means that the common ratio is between minus 1 and 1. But what it also means, and this is why you have if and only if, it means that it works in this direction and this direction. If you have a common ratio that is between minus 1 and 1, then you have a convergent geometric series, and that's probably the more useful way that we are going to be using it, is actually going in the backwards direction, going from right to left. But the if and only if, the I with a double F, means that it works both ways, and we use that a lot in mathematics. So we now know that for it to be convergent, you've got to have a common ratio that's between minus 1 and 1. So if we look just back here, we saw that r here was a quarter. So each time you multiply by a quarter, whereas on this one up here, R was equal to 2. So that's why the bottom one was convergent, whereas the top one is divergent. Okay, so moving on. Let's have a look. This is the formula for working out the sum to infinity. A over 1 minus R. So if we look back at this series here, the bottom one here, then sum to infinity, that means that if you keep on adding up terms forever and ever and ever and ever, you will eventually come to this value. If you just go forever and ever and ever, you eventually come to this value. And in this occasion here, if sum to infinity is A over 1 minus R, then here we had A was equal to 1 and R was equal to a quarter. So you've got 1 minus a quarter, which is 1 over 3 quarters, which is 4 over 3. So there's a quick example of where we use it. So there's the sum to infinity. Let me just go back there in case you might want to, when making notes, is get the formula down and then put this into your notes. It doesn't seem to be wanting to move there. Let's just see if we can go back. There we go. So you might want to get that down once you've got the formula up there first of all. But do make sure you're pausing and making notes. Okay, where does it come from? Where does this sum to infinity equals A over 1 minus R come from? Well, it comes from, whoops, it comes from this formula here, the sum of the first n terms. We used this sum of the first n terms last lesson, and if you remember, this was a formula that we tended to use when we had a value of R that was less than 1, or between minus 1 and 1. So why is that? Well, we'll write it down formally in a second, but just think about it for a second. If you have a value of R that is smaller than 1, say a half, when you square a half, so you do a half times a half, the answer gets smaller. And then if you did a half, say, cubed, you get an eighth. And a half to the 4 is a 16th. So every time the power gets bigger for a value for, say, here a half, the answer gets smaller. And that works for any number that's between minus 1 and 1. So in other words, as n tends to infinity, R to the n tends to 0 if R is between minus 1 and 1. So, if n tends to infinity, R to the n tends to 0, then what we have is a limit. Remember this from first principles when we had to do differentiation. The limit as n tends to infinity of a bracket 1 minus R to the n over 1 minus R is going to be, well, the R to the n, that bit there is going to go to 0. So you've got 1 take away 0, which is 1, 1 times A is A, and so you've got A over 1 minus R. So Bob's your uncle. So there you do. You have the formula there for the sum to infinity of a geometric series if the common ratio is between -1 and 1. Now, how about now we pause for a second and have a bit of a history lesson. Let me tell you about an ancient Greek philosopher called Zeno. Zeno came up with famously 4 paradoxes. A paradox, I think, is best explained through examples. Let me give you an example of a paradox which isn't, I don't think, from Zeno, and that is, keep with the Greek theme, all Greeks are, a Greek man said, all Greeks are liars. Now, it's a kind of statement. A Greek man said, all Greeks are liars. If you sit there and think about it for a bit, it just blows your mind. It's that thing where, hold on, but if he's telling the truth, then they're all liars. But he can't be, because he's a Greek man, and you just get caught in a loop, and there's no way out of it. You can define paradoxes in more formal ways than that, but I guess one way to think about a paradox is something that messes with your head, and whichever way you consider it. Oh, but if he's not a liar, but if he is a liar, then he's being right. So, oh yeah, and you can think about these and consider them and like play with them in your mind and just get like, I can't, it's hurting my head kind of thing. Anyway, but Zeno came up famously with 4 famous paradoxes, and the one I want to tell you about is Achilles. And Achilles, you might have heard of him before as the sulky soldier from the Iliad, kind of spent most of the time not really getting involved in the fight and just staying out of it, not really having anything to do with it, been a bit of a mard, feeling a bit grumpy, and then goes a bit mad at the end and has a fight with a river. Yeah, way to go, Achilles. But here, Zeno has him racing a tortoise. Way to go again, Achilles. You're racing a tortoise. But what Zeno says is that Achilles decides to give the tortoise 100 meters head start. Fairly sure that Zeno didn't say 100 meters, but we will use 100 meters today. So Zeno starts with 100 meters head start. And what happens is somebody fires the starting gun, and Achilles, being the mighty warrior, decides to run as fast as he can, and he makes about 100 meters. The thing is, when Achilles gets to that 100 meters, the tortoise, not being as fast as Achilles, still manages to make another 50 meters. And then Achilles gets to the 100 meters, sees that the tortoise is 50 meters away, runs the next 50 meters. And the tortoise goes 25 meters. And Achilles still hasn't caught him. So now he runs that 25 meters. So, and he runs, that should really be 150. Let's just change that to 175. So we've got a proper axis. That's 175. And then it's 12 and a half. 187.5. The point that Zeno said was every time that Achilles tried to get to the tortoise had moved on. Each time a little bit more, smaller and smaller amounts, but Achilles never catches, or does Achilles catch the tortoise? Now we have a way out of it, and that is to think about this as a geometric series. So if we consider this as the distance that Achilles runs, so we go 100 plus 50 plus 25 plus 12.5 plus ... Now, what we can consider this as is this geometric series that is getting bigger and bigger, and not getting bigger and bigger, it's tending towards a certain value. And if it's tending towards a certain value, eventually Achilles will be at the same point as the tortoise. So he will have caught him. Let's just have a look at how far Achilles has to run before he catches the tortoise. So if we can see here that A is equal to 100, R is equal to a half, then the sum to infinity is A over 1 minus R, which is going to be 100 over 1 minus a half, which is going to be 1 minus a half is a half, times by, so it's 100 times by 2, which is 200. So this kind of math wasn't available to Zeno at the time, but it is a modern solution to this. Wow, Achilles, the great warrior, the one, everyone dipped in the river by his mom, but held up by his heel. Yeah, what a man, managing to catch a tortoise, having a race with a tortoise. Well done. Right, so let's have a look at some examples that come from the textbook. Right, okay, so here we have a, this is example 15 from the textbook. We've got, again, this is very much like the example that we had last lesson, and in that we have the fourth term is 1.08 and the seventh term is 0.23328. So we are going to answer part A by pretty much using the same technique as we did last time. What we're going to do is we're going to set up two simultaneous equations, and then we're going to solve them, find out our value of R, and then hopefully if we get our value of R out, it should be, if it is convergent, between -1 and 1. So let's get started. So the fourth term, remember we write as AR and it's n-1 A cubed equals 1.08. And the seventh term, which is going to be AR to the 6, is 0.23328. Like what we did last time, we don't have to just add and subtract simultaneous equations. We can divide them, and that's what we're going to do here. So we're going to do AR to the 6 divided by AR cubed, and you get, when you do that, 0.23328 divided by 1.08, and apparently when you do that you get 0.216 on this side, and on this side you've got the a's cancelling, r to the 6, r cubed. That leaves you with r cubed, so r equals 0.6, which means that mod r, so whether it's positive or negative, we make it positive, that is less than 1. Therefore, it's convergent. Convergent series. Okay, part B just wants us to find the sum to infinity. Now we had AR cubed equal to 1.08. So we have A times 0.6 cubed equals 1.08. 0.6 cubed, oh yeah, of course it's 0.216. So you've got 0.216a equals 1.08. So a equals 5. Sticking that into the formula for sum to infinity, you've got a over 1 minus r. So you're going to have 5 over 1 minus 0.6, and that leaves us with the grand total of 12.5. So I don't think that example is too different from what we did last on the last section, although it is a bit tricky in this idea that you can divide equations does throw some students. Right, here we go, bit of an easier one, but I would say this time we've got the first term, we've got the sum to infinity. What I want you to do now is pause the video and find the common ratio. Okay, so with this one here, we have a equals to 10. The sum to infinity is 30, and we want r. So the sum to infinity is a over 1 minus r, so you have 30 equals 10 over 1 minus r. So we need to rearrange this now. What I will do is, well, we can, which way we're going to do it? We'll bring the 1 minus r, we'll bring the 30 down, so you've got 1 minus r equal to a third, so that r equals 2/3. Okay, so hopefully you got that, and it was a bit easier than what we had on the last one. Right, okay. Oh, I've missed this question off. What we'll do now is I will go through this with you, and I thought there was something a bit odd there. Make notes on this, and then we'll leave it there for today. Okay, so for a geometric series with first term a and common ratio r, sum of the first 4 terms is 15, and the sum to infinity is 16. So this time we have the sum to infinity is 16, sum of the first 4 terms is 15, so there ain't much more to add on. Once you get to 15, if you're going on forever, and you're going to get to 16. So let's substitute in those values. Let's sub it into, for the sum to infinity equals 16, let's sub in a over 1 minus r equal to 16, and then we have a 1 minus r to the 4 over 1 minus r equals 15. And once we've got that, then we can write a equals, and we're just working on the left hand one, working on this here, that's going to be equal to 16 1 minus r. Now I've got that, I'm going to sub it into this equation here, so we're going to write 16 1 minus r times 1 minus r to the 4 over 1 minus r equal to 15. If you can read, that's 15. The 1 minus r's, of course, will cancel. We'll divide through by the 16, so we'll get 1 minus r to the 4 is 15 over 16. In other words, r to the 4 is the 16th. Now the 4th root of the 16th is plus or minus a half. Now, in part B, it says, given that all the terms in the series are positive, find the value of a. Well, if it was positive, all the terms are positive, You can't have a negative common ratio. So on this, what we're going to say must be r equals to a half, and then we're going to do for the sum to infinity is a over 1 minus r, and we said that was 16. A, we don't know, 1 minus half times by 16 is going to be 8. Right, okay, funny order that I did things in today. Done that slide already. Less examples for me to go through today, but it is quite an interesting topic. There's lots more we can talk about with sums to infinity, but that's where I'm going to leave it today. I'm not going to confuse you. What I'd like you to do now is go away and have a go at exercise 3E, please. Thank you very much.